Greenhouse warming theory is rapidly becoming the most expensive mistake ever made in the history of science. Video 9. Heat is a broad spectrum of frequencies of oscillation whose amplitudes propagate by resonance. For at least 200 years, physicists have considered heat to be a single number that quantifies the amount of thermal energy being transferred per second. Specifically, heat is assumed to be the number of joules of thermal energy flowing per second through some surface, with units of watts per square meter. This thinking of heat as a flux in watts forms the foundation of greenhouse warming theory, which assumes that Earth gets warmer when the amount of heat flowing from Earth back into space is less than the amount of heat flowing from Sun to Earth. Global warming of nearly 1 degree Celsius observed since 1970 is thought to have been caused by increasing amounts of greenhouse gases absorbing more and more amounts of radiation from Earth, decreasing in one way or another the amount of heat flowing back into space by somewhere between 0.6 to 0.9 watts per square meter. This net balance of heat flowing was described by Joseph Fourier in 1822. It seems quite logical if you think temperature of matter is a function of the net amount of heat absorbed. However, as shown in the last video, Planck's empirical law shows that temperature in matter is not a function of amount of heat. Temperature in matter is observed to be a function of a broad spectrum of frequencies and amplitudes of oscillation shown in this diagram. What is most surprising about the current definition of heat as simply a flow of thermal energy is that it totally sidesteps the issue of what thermal energy actually is physically, and why physically temperatures remain constant when there is no heat flowing. The most basic definition of heat is as follows. Heat is what a body of matter must absorb to be raised to a higher temperature and must lose to be cooled to a lower temperature. For example, the heat that Earth must absorb to become as hot as a tungsten filament of a light bulb is shaded yellow in this plot of Planck's law. Planck's law shows clearly that heat, just like temperature, is a function of a broad spectrum of frequencies of oscillation, each with an amplitude of oscillation that is determined both by the temperature and by the difference in temperature. Physics is about what is physically happening in nature. How is it physically that a flow of heat causes the temperature of a body of matter to change? When Planck worked out his law in 1900, he found it useful to postulate that thermal radiant energy E is equal to a constant h times frequency nu, the Greek letter nu. This simple equation, E equals h nu, says that the energy of oscillation for a frictionless oscillator is equal to some scaling constant h, known as the Planck constant, multiplied by a frequency of oscillation. Thus, frequency of oscillation physically is the same thing as energy of oscillation. Energy of oscillation physically is the same thing as frequency of oscillation. This simple equation is now known as the Planck-Einstein relation, and is the universally accepted way to calculate the energy of oscillation at each frequency of oscillation throughout the whole electromagnetic spectrum, ranging over 20 orders of magnitude, from radio signals at cycles per second through infrared, visible, and ultraviolet frequencies to X-rays and to gamma rays at 100 million cycles per second. The concept of energy in physics has a long history and is still not crystal clear. Energy is what causes things to move or to change. Planck's law shows us that absorbing or emitting a broad spectrum of thermal energy causes temperature of matter to change. This change in temperature is proportional to a change in amplitude of oscillation at each and every frequency of oscillation. Absorbing an individual frequency of energy, E equals h nu on the other hand, typically causes change in the amplitude of oscillation of certain bonds. If this individual frequency of energy is high enough, it's observed to cause chemical changes, ranging from the photoelectric effect to a change in the configuration or even the destruction of certain chemical bonds holding matter together. This figure shows Earth's annual energy budget calculated using the widespread assumption that heat is additive. Incoming and outgoing heat are added together to determine that the net heat absorbed is 0.9 watts per square meter, shown in the white ellipse at the bottom center of this figure. This net heat absorbed is assumed to be the cause of observed global warming. Temperature, which is the result of the flow of heat, however, is not additive. If you take two bodies of matter that are identical in every way except in temperature and connect them together so that heat can flow, the final temperature, assuming no losses, will be the average of the two initial temperatures, not the sum. Temperatures are not additive. They are averative, a word I coined to specify the averaging that is observed to be physically happening in nature. Furthermore, heat flows in a manner that is averative. The black line in this graph shows the increase in temperature measured every 10 seconds for a small piece of black metal 3 feet away from a light bulb after the light bulb has been turned on. The red line shows the temperature calculated by adding 4.6% times the ending temperature of 28 degrees Celsius minus the existing temperature at each 10-second interval. The two curves are identical. The 4.6 is a function of the conductivity of both surfaces and the rate heat is being lost by the piece of metal. All curves of warming and of cooling have this distinctive asymptotic shape where the flux, the change in heat per second, the change in temperature per second, decreases with the difference in temperature in an averative way. How does averaging occur in nature? How does the rate of warming or cooling know the final temperature of 28 degrees in this case? The answer is resonance, also known as sympathetic vibration. Resonance is a fundamental physical property of oscillating systems that is widely observed throughout nature. When two oscillators are oscillating at the same frequency, the oscillator with a lower amplitude of oscillation is observed to gain amplitude of oscillation, while the oscillator with the higher amplitude of oscillation is observed to lose amplitude of oscillation. In an ideal case, both oscillators end up with identical amplitudes of oscillation, which is the average of the two identical amplitudes of oscillation. In this way, amplitudes of oscillation flow spontaneously from higher amplitude of oscillation to lower amplitude of oscillation. Furthermore, every oscillator has certain natural frequencies of oscillation based on its size, mass, and configuration that are called resonant frequencies. When an oscillator is caused to oscillate at one of its resonant frequencies, the amplitude of oscillation can become very large, especially when the oscillator has very little or no friction, as is typical for oscillation of all the bonds that hold matter together. Resonance occurs when two oscillators are physically touching in some way. The simplest example is when you push a child on a swing. If you push at the same frequency as the frequency that the swing is swinging, the amplitude of frequency of oscillation of the swing will increase. Push at any other frequency and the amplitude will decrease. Another example of resonance is when you take two tuning forks and strike one so it rings. The other will start ringing. They are interconnected by the sounds causing changes in air pressure. This is the same way that certain hair cells in the cochlea of your ear resonate to sounds that you hear, allowing your brain to distinguish different frequencies of oscillation. Resonance is also observed to occur across air and space via line of sight by what we think of as being electromagnetic radiation. Electric currents on the surface of the antenna of your favorite radio station are caused by the transmitter to oscillate at the frequency assigned by the government to that radio station. You tune your radio receiver to resonate at that specific frequency, causing your receiver to receive that specific station with much greater amplitude of oscillation than all the other radio signals that are occurring simultaneously. In the same way, thermal energy is transferred by simultaneous resonance at each and every frequency of oscillation. Resonance is observed to happen at any distance in direct line of sight, but the density of cells on the surface that can resonate decreases with the square of the distance, making the radiation appear fainter. Fewer cells resonating means they have to share their amplitudes of oscillation with other cells on the surface. You see via resonance. Visible light has very high frequencies that are close to the natural resonant frequencies of 3 types of color-sensing cones in each of your eyes. Each type of cone is most sensitive to a particular part of the spectrum that, for simplicity, we will call red, green, and blue. Each of these cells resonates with different amplitudes of oscillation in response to a particular incoming color. The 3 amplitudes are sent as signals to our brain, which combines these 3 signals to distinguish approximately 10 million different colors. The RGB monitor of your computer does something similar, combining 3 different shades of red, green, and blue digital signals sent by the computer to allow each pixel to display one of nearly 17 million different colors. Each color has an intensity or brightness, which physically is the amplitude of oscillation of the oscillator producing that specific color. Thermal energy is a simultaneous resonance of all frequencies of oscillation in the infrared, visible, and ultraviolet spectra, transferring amplitude of oscillation in an avertive way, warming the absorbing body and cooling the emitting body. Current concepts of heat, radiation, and radiative forcing are additive, but we observe in nature that they are avertive, which can only happen in nature via resonance. Heat physically is not a single number of watts per square meter, as assumed today in climate science and in physics. Heat is observed to be a broad spectrum of frequencies of oscillation, whose amplitudes of oscillation propagate via resonance. Thank you.